Hi, I'm Aman Arora from the University of Texas at Austin. I'm excited to talk to you about our paper titled CoMeFa, Compute and Memory Blocks for FPGAs. Let's get started. FPGAs are increasingly being used for accelerating modern workloads like deep learning. FPGAs have configurable logic blocks, hard math units called DSP slices, and memory blocks called BRAMs. BRAMs are the storage houses of FPGAs, and the amount of on-chip DRAM in FPGAs is growing very fast. To begin to motivate our work, we make some observations on how BRAMs are used in FPGAs and pose some questions. First, when using BRAMs, the data stored in them has to travel through the routing and interconnect wires to reach the compute units. But can we avoid this and save some energy and routing congestion? Secondly, we observe that the number of bits accessible per clock inside a block RAM is typically higher than that available outside the block RAM, because the physical number of bit lines is higher than the number of available ports. So we ask the question, can we utilize this higher bandwidth somehow? And thirdly, BRAMs may be left idle if not required by the application. The limited heights and widths offered by block RAMs also cause underutilization. So the question is, can we increase the utilization of BRAMs in applications? Applications like deep learning, which are commonly accelerated using FPGAs, need flexible precision. int4, 8-bit floating point, even binary are common. But DSP slices only support a few hardened precisions. Can we increase the silicon area that supports custom precisions? And finally, workloads like deep learning are very compute intensive and have a lot of parallelism. Can we increase the silicon area that provides this compute capability? To answer these questions, we introduce new blocks called CoMeFa. Basically, we propose incorporating the principles of bit serial computing and compute and memory into block RAMs in FPGAs to convert them to CoMeFa RAMs. Having introduced the motivation of our work, let us look at some of the prior work. Computational RAM is an architecture from the 1990s where a row of processing elements was added to the memory. More recently, researchers from the University of Michigan designed SRAMs where multiple word lines are activated together and logical AND of the bits in the activated rows can be read at the sense amplifiers, thereby performing logic in memory. This has robustness issues and involves modifying SRAM's internal operation. That technology was extended and processing elements that primarily perform 1-bit addition were added to the memory by researchers. This technique was proposed to be applied to FPGA BRAMs in this conference last year. This was shown to provide benefits for DL acceleration. We refer to that architecture as CCB in this presentation. Let's now dive into the architectural details of CoMeFa RAMs. Let's start with the basics. CoMeFa blocks perform computation inside the RAM, thereby converting a block RAM into a highly parallel SIMD engine. This avoids moving data through the routing wires and increases the compute throughput of the FPGA. A configurable processing element is added near the sense amplifiers. This PE, or processing element, can perform any 2-bit function and more. It is very flexible. We realize that the block RAMs on FPGAs already are dual-ported. We use this dual-port nature of BRAMs to read out 2 rows containing operands at the same time, so we do not need activating 2 word lines on the same port like in prior work. The PEs added to CoMeFa RAMs are 1-bit bit serial processing elements. This makes them precision agnostic, which is great for applications like deep learning. Even floating point operations can be supported, making the blocks versatile. And finally, the computation is done using the physical width of the block RAM. This increases the effective on-chip memory bandwidth available to the applications. We see the CoMeFa RAMs as blocks that fuse the advantages of various existing FPGA blocks: storage capabilities of block RAMs, custom logic capability of logic blocks, and hard math from DSP slices. Let's see how we build a CoMeFa RAM by looking at a standard VRAM first. The baseline VRAM we use is from Intel FPGAs. The size is 20 kilobit and the column muxing factor is 4. there are 160 bit line pairs, 128 word lines, and 40 sense amplifiers for each port. The memory cell array is at the center. Then there is the peripheral circuitry, decoders, sense amplifiers, etc. for the first port, the same peripherals for the second port, and then eventually the crossbars to interface with the FPGA routing. Three parts of this VRAM are modified for CoMeFa. These are shown with red boundaries here. Firstly, we add processing elements near the sense amplifiers, and in some cases also add sense amplifiers. Then we add some logic like comparators and muxes to decode the instructions sent for computation to the CoMeFa RAM, and also a configuration RAM cell to decide the operating mode of the CoMeFa RAM. And finally, we make some modifications to the control logic to have one clock cycle that does read, compute, and write. We explore and propose two architectures of a CoMeFa RAM block. CoMeFa D is the delay optimized architecture, and CoMeFa A is the area optimized architecture. In CoMeFa D, we add additional sense amplifiers, and one PE is added below each column, so there are 160 processing elements. All columns are read and written in parallel in one cycle. The clock period is slightly increased compared to a baseline VRAM, and there is high area overhead because of the additional sense amplifiers and processing elements. CoMeFa A, on the other hand, does not require any additional sense amplifiers. One PE is added below each multiplexed column, so there are 40 processing elements added. And we use a technique called sense-am cycling, in which we cycle through the 4 columns behind a column mux sequentially in one clock cycle. The clock period is increased more than CoMeFa D's increase, but the area overhead is much lower. It is important to mention here that CoMeFa D is more practical than CCB because multiple word lines are not activated simultaneously on a port, and voltage reduction is not required for robustness. CoMeFa A is more practical than CoMeFa D because of the low area overhead and because it retains column muxing. There are two modes of operation of a CoMeFa RAM which can be selected at configuration time. In memory mode, the CoMeFa RAM behaves just like a normal VRAM. In hybrid mode, the CoMeFa RAM can be used for compute as well as storage. In this mode, the data written to the address 1FF is treated as a compute instruction by the CoMeFa block. Let's see how a CoMeFa RAM operates at a high level. In this diagram, we show two operands of 160 4-bit elements stored in a transposed manner. Instruction generation logic, which is implemented in soft logic, sends an instruction every cycle to the memory by writing to the special address 1FF. The instruction tells the RAM which rows to read, which compute operation to perform on the data, and which rows to write back. In each such cycle, what happens inside the RAM is this. The operand rows are read, one row on each port, one bit of all 160 elements is read. The PE performs the computation, and the result, again one bit for 160 elements, is written back to another row. This is repeated for multiple cycles, eventually performing a multi-bit operation involving multiple rows. Let's now look at how the processing element of a CoMeFa RAM is constructed. First, CoMeFa D. We showed the sense amplifiers for the 2 ports and the write drivers for the 2 ports in the block RAM. To this, we add a multiplexer to enable any function of 2 inputs. This multiplexer is called the truth table mux. Then we add logic for sum and carry operations. Multiplexers are added to select what to write back. And there is a mask latch, which is typically used for predication, and a multiplexer which decides which signal will be used for predication. The processing element for CoMeFa A is a little bit different than CoMeFa D. It has 4 carry latches, 4 mask latches, and 4 sum latches. On the top, you can see that there is one sense amplifier per 4 bit line pairs, brown, green, red, and purple. On the right, you can see the timing diagram. In one clock cycle, each bit line pair is read back to back and computed upon. The results are stored in the respective latch one by one, and then the results in these latches are written back. The process of sense-am cycling enables us to perform 4 operations in a clock period that is 2.5 times the baseline instead of taking 4 clock periods. In the description so far, we have said that both operands are present inside the RAM block. But consider an example where we want to multiply the elements of a vector with a scalar. In this case, if we keep the scalar operand inside the RAM, it will have to be replicated for each column, as shown in this diagram. However, we can save space inside the RAM by keeping this operand outside in soft logic, and instructions sent to the RAM can be modified accordingly. The instruction generation logic can even inspect multiple bits of this operand, enabling us to implement optimized algorithms like Booth algorithm for multiplication. This utilizes the truth table mux in the processing element that we saw earlier. We were able to see a speedup of 2x for dot product operations using this method compared to the baseline repeating add method of multiplication and addition. So the overall benefits of CoMeFa are a combined effect of the hardware architecture as well as efficient mapping and algorithms deployed for CoMeFa. Let's look at the methodology that we used to evaluate CoMeFa RAMs. We used academic tools like VTR and CoFee for FPGA architecture exploration, and also commercial tools like Synopsys HSpice and Synopsys VCS for performing simulations. The baseline architecture used for our evaluation is similar to Intel Arria 10 FPGA. It is a modern island-style FPGA with columns of logic blocks, block RAMs, and DSP slices interspersed in routing interconnect. This table shows the number of various types of blocks on the FPGA. We created 3 architectures to compare this baseline FPGA architecture to. One where BRAMs were replaced with CoMeFa DRAMs, the second where we replaced BRAMs with CoMeFa ARAMs, and third where we replaced BRAMs with CCBRAMs. We use 6 benchmarks across various application domains ranging from deep learning to signal processing and beyond. We created different scenarios within these benchmarks. Some benchmarks like GEMV and FIR filter were compute bound, some were DRAM bandwidth bound like element-wise multiplication, and some were on-chip memory bound like bulk bitwise operations and reduction operations. And different precisions were also used to show the versatility of CoMeFa blocks. Let's look at the results from our evaluation now. To begin with, here is a qualitative and quantitative comparison of the various types of compute and memory blocks for FPGAs considered in this study. To highlight some of them, CoMeFa blocks do not activate multiple word lines at the same time on one port, but they use the dual port behavior of block RAMs for computation. The processing element in CoMeFa is generic and flexible. The area overhead at the chip level for adding these blocks is 2.5% for CCB, 3.8% for CoMeFa D, and 1.2% for CoMeFa A. Finally, CoMeFa A is the most practical to implement, and CoMeFa D is medium practicality among these options. Let's see how much improvement in compute throughput can be obtained by adding CoMeFa RAMs to an FPGA. This chart shows the compute throughput obtained from various components of the FPGA for MAC operations for various precisions mentioned along the x-axis. The gray color shows the throughput from logic blocks, the lighter green color shows the throughput from DSP slices, and the 3 bars on top show the additional throughput from RAM blocks, CCB, CoMeFa D, and CoMeFa A. CoMeFa blocks significantly increase the throughput of the FPGA up to 2x in some cases at a very small area overhead. The throughput reduces as the precision increases, as can be seen in this chart. Here we show the speedup obtained for various benchmarks we mapped to the FPGA. For compute-bound benchmarks, speedups of up to 1.8x were seen. There is an asterisk next to the element-wise multiplication benchmark because this is a benchmark that was DRAM bandwidth limited, and CoMeFa RAMs are not targeted to improve DRAM bandwidth. The speedup shown here is for the case when all the compute units on the FPGA could be fed with data. The on-chip memory-bound benchmarks show much higher speedups. Overall, we see a geo-mean speedup of about 2.55x for CoMeFa D and 1.85x for CoMeFa A. Now let's see the reduction in energy obtained by using CoMeFa RAMs for computation. The compute-bound and memory-bound applications are not expected to see energy reduction because more compute hardware is used to obtain the speedup compared to baseline. This chart shows the on-chip memory-bound applications on the x-axis. The energy consumption in the baseline FPGA is shown in red. We use an energy model that accounts for wire energy as well as transistor energy. We see that the energy reduction of up to 56% can be obtained compared to baseline FPGA. This happens because of reduced logic area as well as reduced routing wire length. Let's now conclude this discussion. In this paper, we proposed changing block RAMs on an FPGA to CoMeFa RAMs, which are new blocks that fuse computation and storage capabilities into one block. We saw that using CoMeFa RAMs, we can speed up multiple applications by increasing compute throughput while also reducing energy consumption at a very small area cost. To the best of our knowledge, this is the first work to utilize dual-port nature of block RAMs for compute, deploy a configurable 1-bit processing element, and apply compute in memory to FPGAs for non-DL applications. Thank you. Please reach out to me for any questions that you may have.